Welcome to the lectures on fundamentals of MIMO wireless communications. We have started to discuss diversity performance. We have seen selection combining. We have also seen maximal ratio combining. We have seen one way of calculating error probability. I'd also like to show you two different ways of arriving at the same error probability expression. So that would be one of the most important goals of this particular lecture. So before we start on with the error probability expression for maximal ratio combining, I'd like to draw an equivalence between two kind of descriptions for typical error probability expressions so that things are less confusing in all future things that we do. So to begin with, let us consider a BPSK system where we have one symbol at minus root EB and another symbol at root EB, and this could also be written as A. So for this situation we can always write that the D min, that is the minimum distance between the constellation points for this simple case, is equal to 2 root over EB, which is also 2 times A. And for this case, if we were to write the expression of SNR, signal to noise ratio, for PPSK it is gamma B, that is SNR per bit. This is equal to square root of EB, that is this value, squared divided by sigma squared n, which is the noise variance, and this is basically EB by n naught. This is the expression which we are more used to. Now this is equal to A squared, because root EB is A by sigma squared n, which is equal to EB by n naught. Now given these things that we have, definitely we could write EB by n naught is equal to A squared by sigma squared n, or A squared equals to EB. Generally we have error probability expression for AWGN as Q function of square root of 2 gamma B, which is Q function of square root of 2 EB by n naught. In some cases you might find error probability expression is also given as Q root over D min squared by 2 n naught. This expression is also used in many places. So if we expand this expression, we're going to get root over D min squared is basically D minimum is 2A, that means 4A squared divided by 2 times n naught, which is Q of square root of 2A squared by n naught. And since these probability expressions would be the same, so that means the argument of this must be the same, and also we find it clearly it's the same if you take out 2 and 2. EB by n naught should be equal to A squared by n naught, and we have here also EB by n naught as A squared by n naught. So if you look at these two expressions, this is equal to EB by n naught, gamma B is also equal to EB by n naught. So this we could also write it as Q of square root of 2 EB by n naught, which is equal to Q of square root of 2 gamma B. In other words, this expression is the same as this expression, so we need not be confused. And just to draw the equivalence for quick reference later on, D min squared by 2 n naught is equal to 2 gamma B. So this means this is equal to 2 EB by n naught, or if you cancel out n naught from both the sides, you have D min squared is equal to 4 EB. Now this is again well established from here. If you see D min squared, if I take from here, I would get D min squared is equal to 4 EB. So the same expression holds. So basically under this circumstance everything holds true. So we are just using this to show that either this expression or this expression, all of them are correct and they will be used as and when applicable. Generally speaking, we would use probability of error expression as is an approximate expression, C1 e to the power of minus C2 gamma. Gamma is the SNR. So I would say probability of error because this is sometimes written as probability of symbol error and sometimes probability of bit error, depending upon what we are interested in. In all cases, this kind of expression is typically used. This is an approximate expression coming from Chernoff bound. So, and this is very, very useful whenever there is an exponential function. Usually the relationship between PS and PB for gray coding is PS divided by number of bits is equal to PB. This is again an approximate expression. So these are some of the things we should keep in mind when we'll be using the error probability calculations. So now moving forward with this is the error probability for MRC. We have already done one, and again we will use the Chernoff bound. So the Chernoff bound tells us that Q of x is less than or equal to e to the power of minus x squared by 2. So this basically leads to the earlier expression that we had, that error probability expression looks in this form. We'll take a look at that. So probability of error, symbol error, is given as alpha m q of, this is what I was explaining, root over beta m, and gamma I would put a summation indicating that of an MRC. So this is less than or equal to alpha m e to the power of minus beta m gamma combination by 2. So if you look at this expression that we had written here, this is similar in form over here, where C1 is equal to alpha m and C2 is equal to beta m by 2. So this is a typical form that is very, very useful. And in our case, this is equal to alpha m e to the power of minus beta m by 2, and this gamma sigma that we have written is basically I equals 1 to m gamma I, where gamma I is the SNR experienced by each branch. And as usual, we are going to calculate the PS, that means average probability of error for MRC. To do that, it is 0 to infinity the probability of error, symbol error, as a function of gamma sigma. Right, this is a function of gamma sigma, you can clearly see that, times P, that is the probability density function of gamma sigma, times gamma sigma d gamma sigma. Now for simplicity, we would take off this gamma sigma, and if you look at this particular expression, there is PDF, probability density function of the joint, probability density function of the gamma, that is summation of gamma I. What we ideally need is the joint distribution of all these gammas. Now if we take independent branches, that means all these branches are independent, that is as we have said earlier, that will make that assumption for getting insight into the results, then the joint distribution is basically product of distributions, and that is what we are going to exploit in both the cases. So what we are going to have is, if I look at this expression, it is alpha m e to the power of minus beta m by 2, and the summation that I have, I could write it, or I could say gamma I, and there's a product of it, or so I've taken one of them, integrate 0 to infinity. Now I take this, the particular one corresponding to gamma I, 1 by gamma bar, the average SNR in that particular link, which is again the same for that link, gamma I by gamma and d gamma I. So this is for one of them, and since P gamma sigma is basically product of all the gammas, we will have again P gamma, if this is gamma 1, this is gamma 1, P gamma 2, d gamma 2, again integrate 0 to infinity, and so on, all of them, and these will be m in number, and for each one, see here we have this e to the power of minus beta m by 2 gamma 1. So here we are going to get, or in the second one we are going to get e to the power of minus beta m by 2 gamma 2, and so on and so forth. So for every of the integral we are going to get that. So to get to the error probability, we need to solve one of these integrals. One of those integrals, if you solve them, you're going to get alpha m, of course, it comes out. It is 1 by gamma bar e to the power of minus beta m by 2 plus 1 by gamma bar divided by minus of beta m by 2 plus 1 by gamma bar, limits 0 to infinity. So if you work this out, you're going to get this as 1 upon 1 plus gamma bar beta m by 2. If I take out gamma bar, this gamma bar and the gamma bar I take out over here cancels with each other. So this is the particular expression that we are left with. And then what we would be having is 1 by 1 plus gamma bar beta m by 2. This is the result of one of the integrals, and since all of them are identically distributed, all these p gammas are identically distributed, we'll be getting again those factors multiplied with each other. So effectively what we'll be getting is raised to the power of m, because there are m such integrals. Alpha m is outside, and if you make the approximation that gamma bar is much greater than 1, that means average SNR is pretty high, this could lead to alpha m and beta m by 2 gamma bar raised to the power of minus m. So this is again the same expression that we have got. This expression as well as this expression are the same expressions. So all we are trying to say is by the earlier method or by this method, you are able to get to the same result. What we will now do is show you another way of doing the same calculations, so that you are well conversant with these techniques, which you can apply in other situations, which is not being covered in this particular case. So again, let us take a look at gamma sigma. Gamma sigma is basically I equals 1 to m gamma I, that means summation over gamma I, and the PS expression, of course, we take the same PS expression, C1 e to the power of minus C2 gamma S, so or gamma sigma, whatever it is, and so what we have taken is basically alpha m e to the power of minus beta m by 2 gamma. This is the expression we have taken, and again PS bar is equal to 0 to infinity. We're going to apply the same thing, e to the power of minus C2 gamma P gamma sigma gamma T gamma. Basically this distribution is for the combined SNR, and if we assume independence, that means if we assume that the joint distribution of all these SNRs are independent, so we're going to get P gamma 1 of gamma 1 multiplied by P gamma 2 of gamma 2 and so on up to P gamma m of gamma m. This is what we exploited in the earlier method. So again, carrying on with the same thing, we're going to get C1 integral 0 to infinity m of them, m number of them, e to the power of minus C2 sum over gamma I equals to 1 to m P gamma 1 times P gamma 2 up to P gamma m d gamma 1 d gamma 2 up to d gamma m. This is what we have done till now in the previous case. So at this point, again the same thing that we'll use. This particular expression, you could write it as equal to product of I equals to 1 to m e to the power of minus C2 gamma I. So these two expressions are equivalent, so hence we could use this expression, and that is what we have precisely done. But here we'll use a slight modification compared to the last expression, the last method that we did. So we have, I'll write down the integral again, m number of such integrals. Here product of I equals to 1 to m e to the power of minus C2 gamma I. This is the product P gamma I d gamma I. So this is a more concise way of writing the expression. And if we now focus on one of the integral, let us see how does it look like. This product sign, I can bring it outside as we have done before. C1 is of course outside. I equals 1 to m integral 0 to infinity. This is precisely what we have done in the previous. So till now the steps are remaining the same. There is no modification, and this particular expression, now if you observe this is where we make the slight variation. The result is going to be the same, but still the way we could do it is different. If you look at this expression, it reminds us of moment generating function, where we say the moment generating function s of gamma, let's say, is equal to expected value of e to the power of s gamma. That means the expectation of e to the power of s gamma, this is a function of s and we are taking the random variable gamma. So this is 0 to infinity, that is the range of gamma. Expectation means p of gamma e to the power of s gamma d gamma. This is the expression. If we look at this expression now, it is precisely the moment generating function where s is equal to minus c2. So if we have this result already derived, that means if we have the moment generating function and we can see that we are using a moment generating function here, then we could exploit that expression and we could get it. So for our case, we have e to the power of s gamma is basically 0 to infinity e to the power of s gamma p gamma d gamma, and s is equal to minus c2. This is what we have already said. So if you use this p gamma as 1 by gamma bar e to the power of minus gamma by gamma bar e to the power of s gamma d gamma integral 0 to infinity, again we have the same thing. The result is 1 by 1 plus c2 gamma bar. This is the expression that we have. So this expression now we can substitute over here. So what we get is c1 m times 1 by 1 plus c2 gamma bar. So m times the same thing is this. Again, if we remember what is c1, we have alpha m 1 by 1 plus beta m by 2. c2 is beta m by 2. That's what we have identified here. If you see, c2 is basically beta m by 2. So that is what we'll be using. So we have it raised to the power of m. Again the same expression for large gamma bar approximation. This will become alpha m beta m gamma bar by 2 raised to the power of minus m. So what we have essentially done is done it in different ways, and still we arrive at the same expression of probability of error. So the main idea of doing this particular thing is that you are able to use these techniques wherever which one you find more applicable, and you can calculate the probability of error for the appropriate scheme that is under consideration. With this, we'd quickly start or take a look at the general diversity, that is what the general order of diversity or general way of doing diversity. That is, if we look at if we try to analyze a typical diversity system, we will say that there are m number of links between a transmitter and a receiver. M number of links between a transmitter and a receiver, and the first link has a channel coefficient h1, the second link has a channel coefficient h2, like that. The last link has channel coefficient hm, and we have 1, 2 up to m receivers. So basically yi is the ith received signal, and from the transmitter we are sending root over es upon m as the signal energy or the signal power per transmit branch. So when we are doing transmit side diversity, that means you can consider time diversity, frequency diversity, or even spatial diversity. When we are doing diversity from the transmitter side, a general diversity, that is what we can consider. We have this particular thing at hand. So that means the power is done in such a way that the total power at the transmitter remains as es. So if you take the square of this, you're going to get es upon m as the power of any one of the branches multiplied by m number of branches. So basically the total power is es. That's indicating that the total power of this system is not different from the case where I have a single input and a single output case. So this is a primary assumption which we will make. So the received signal yi is equal to root over es upon m times hi s plus ni. So this is pretty straightforward. Hi is the channel coefficient, s is the signal, and n is the noise. Noise is zero mean, circular, symmetric, complex Gaussian. This is what we have already described before. and sigma squared ni is equal to sigma squared n. That is typically what we use for noise, and it is n naught, and of course we have expectation of ni nj conjugate is equal to 0. So that means they are uncorrelated, they are independent, it's Gaussian. So these typical assumptions as we have made earlier also holds true. And at the receiver we would like to maximize the SNR, so we would say that I would like to have a combiner such that the received signal Z is formed by I equals 1 to m hi conjugate yi. This means I have knowledge about the ith channel, which is hi. So I have knowledge about the ith channel, which is hi, and I use it. I take the conjugate, multiply by yi, and I get it. So if you expand this expression, you're going to get I equals 1 to m yi. Of course, we will have root over es upon m mod hi squared s plus hi conjugate ni. This is the expression you're going to get. So we are adding up all of these terms. If we write eta as the expression of SNR, then we are going to get the square of this term divided by the square of this term given h. So we'll be getting 1 by m square of this, and sum over I equals 1 to m mod hi squared es by n naught, e of s by n naught, and this you would often write it as rho, so you could write it as 1 upon m, and if you would look at whatever is this is basically the Frobenius norm of h squared times rho. So this is the SNR expression that we have at the receiver for this particular scheme, where we're dividing the power equally amongst all the transmit branches, so the total power remains the same as this. So with this, again we'll be using the Chernoff bound mechanism to calculate the error probability. So so of course q of x is less than or equal to e to the power of minus x squared by 2. So I'm writing it often so that we remember this is the one that we'll be using. So given this, probability of error is less than or equal to ne bar. This means this is another approximation for error probability, but if you look at the expression, it's pretty similar to what we have. Ne bar effectively means I would give probability of error approximately equal to ne bar times q of root over d mean squared by 2 times eta. So ne bar is the nearest minimum distance of separation. Sorry, this is the number of nearest constellation point, number of nearest constellation points. So in case of BPSK it is 1, in case of QPSK it is 2, and this is the minimum distance to nearest neighbors. Right. So we have given this kind of an expression before, and eta is the SNR. So basically in case of AWGN channel it is es by n naught, and in our case we have channel coefficient also multiplied with that. So given this, we could write probability of error with this approximation is less than, we'll expand the full of this is rho by 4 m d mean squared and hf squared. Just look at it carefully. So eta, the expression that we have, eta is rho by m, okay. We have rho by m, hf squared, that is hf squared, d mean squared, and 2 multiplied by this 2 is 4. So basically rho by 4m d mean squared hf squared. So this is the error probability expression, and now we can use our earlier result. So basically what we want is PE bar, average error probability. So again we'll be using the moment generating function, because earlier we had said expectation of e to the power of s or nu hf squared, we had used a negative sign there, is equal to 1 by determinant of I, the dimension of this, in this case it is m, plus If I use a plus, I use a minus over here. If I use a minus, I'll get a plus over here. Nu times r, so that would be 1 plus product of I equals 1 to m. In this particular case, 1 plus plus or minus depending upon what we have, nu times lambda of r, lambda I of r. So when it is independent, when h are independent, we are going to get these eigenvalues as all ones. So what you'll be left with is the average SNR. So when you're left with the average SNR, you could write the average probability of error to be the expectation over this. So we'll have the product I equals 1 to m, because this is of size m and the maximum size is of size m. 1 plus rho, rho is basically rho d mean squared by 4m. This whole term is basically mapping to our nu in this expression, or s, whatever you'd like to use, and that of hf squared is basically 1, because again remember we have mod of hf squared equals to 1, and these are of eigenvalues, so this is outside this, this is getting multiplied with all of these eigenvalues, so this is 1. So we have this expression. Now this you could further say is equal to, or this is equal to any bar times 1 by 1 plus rho d mean squared by 4m raised to the power of m. And for large rho, when SNR is large, this is approximately equal to any bar rho d mean squared by 4m raised to the power of minus m. So once again you're seeing that it is with diversity, the error probability expression is raised to the power of m, and the error probability decreases because of these diversity branches. So we stop at this point in this particular lecture with this expression, and in the next lecture we are going to see that what is the significance of this expression and what we can understand more of diversity from a typical expression of this, and what else this expression can help us in future to get expression of error probabilities or understand things in a better way. Thank you.